Next is example 19. A pilot executes a loop-the-loop. What is this? So it's just one loop, basically. Okay. Recently, there was a DSTA air show. No, DSTA is a Singapore air show. Right? Lots of planes doing very interesting maneuvers. Yeah. Current technology for fighter planes is that, I mean, if you are interested in war technology, is that the tighter the airplane can spin, the better the fighter plane. Right? Because if you take very long to curve, your enemy can do it in a short curve. He can come behind you and attack you. Right? So most technology tries to have that kind of technology. So there are some designs in airplanes that actually can hover like a bird, like a hummingbird. So you can fly and then stop. Then your enemy will rush past you, then you're behind, and then you go and poke the backside, right, with your missiles. But anyway, back to this. Executes a loop-the-loop in this maneuver is moving at a radius, a vertical radius 2.7 kilometers. It's pretty huge, right? The diameter is 5.4 kilometers. And it's moving at a constant speed of 225 meters per second, close to the speed of sound. Determine the force exerted on the seat of the pilot at the bottom of the loop and at the top of the loop. So I just want to ask a simple question without looking at the answers. Where do you think there's more force? At the bottom or at the top? Exerted on the seat of the pilot. So to answer this question, right, you have to tap into your own experiences. Right, Olympiad, when you answer a question, you try to tap in. Have you sat in a roller coaster before? No. Okay. When you are free, there's the USS, right? You can go and try. Huh? It's not that good, is it? Yeah, I know, America, the Six Flags and all that. I'm not sure China has any more new tech. I'm sure you all can build crazier stuff, like more powerful technologically. But in your experience of a roller coaster, when you are curving up, do you feel like you are heavier? Right? Even in a lift, where the lift is accelerating up, you feel heavier. When you're at the top and you're upside down, naturally the weight intuitively should be less. So even without thinking further, right, we can have a sense of the magnitude of the answers. So let's look at this. At the bottom, because you are moving at a constant speed, there must be a net force upwards, which means the force at the bottom must be larger than the weight, so that the net force is pointing to the top, or rather to the middle of the circle. So using this, we know that the net force is equal to mv squared over r. We have rearranged, we can get this. At the bottom, however, the weight and the normal reaction force must add up to become the centripetal force, which allows us to have this, right? So you see that at the top, the contact force is actually less than what I'm feeling now. If I am the fighter pilot, the normal reaction force I'm experiencing now is more than what he's feeling at the top of the circle, right? So is there a minimum velocity that he can go? That he must go before he falls off the chair, or before the seatbelt tries to hold him back? There is, right? Because if your v squared over rg becomes smaller than 1, your n top becomes 0 or negative, which is strange because it should not be negative. Right? If it's negative, it means that you need to have a seatbelt to hold yourself back. Okay, so there is a minimum velocity that he must go at the top. Right. Next, non-uniform circular motion. So just now what I explained in the vertical motion is uniform. That means it's the same speed here, everywhere. Non-uniform circular motion, what in your experience would that be? Have you watched the circus and there are some people who swing in a swing that becomes higher and higher and higher, then it goes full circle. And the movement will look like my finger. You'll be Fast at the bottom and slow at the top. Fast at the bottom and slow at the top. Right? So that's what you call the non-uniform circular motion, but it's still a motion, it's a full circle. How does that work? Okay, in a non-uniform circular motion, there must be both radial acceleration, that means acceleration in the radial sense, and acceleration in the tangential sense, tangent to the circle, which means the velocity will both change direction and change magnitude, which will make sense. Okay. Awesome. I should have brought my jacket. So a small sphere of mass m is attached to the end of the chord of length r and rolls in the vertical circle. Determine the tension in the chord at instant where the speed of the sphere is v, and the chord makes an angle theta with the vertical. So using this, you can resolve the weight into two components. You see, so now that is non-uniform, you have to resolve the force in the radius of the circle. That's a trick. Right? You resolve it radial and perpendicular to the radius. Right? That means in the radius and tangential directions. You see that T must be equal to mg cosine theta because the circle, right, is always at a fixed length away from the center. T and mg cosine theta must be equal. Oh, that's the learning point. And mg sine theta will then be the acceleration tangentially. Right? Oh, sorry. It's not T equals mg cosine, it's T minus mg cosine theta equals to mv squared over r. And mg sine theta is equals to ma. My bad. Okay. Because if T is equals to mg cosine theta, it will go in a straight line. Oh, sorry about that. Putting these two together, then you can actually find that the tension is equal to m bracket v squared over r plus g cosine theta. Not a big problem, I think. Special cases at the top and bottom, right? You have your angles to be theta, cosine 180, or 0. You have these two ideas. Okay, which is what we did for. Well, this is not what we did for the airplane, but which is what we actually ask very often for H2 students. In H2, we generally ask the top and bottom. We don't ask at various angles. But for Olympiad, we go the extra mile. We give you this equation for at all angles theta. Okay. Right. Finally, we can talk about gravitation. We still have 8 minutes. You still have 8 minutes, huh? Kepler's law. Straight away, Kepler's law. Before Kepler's law, we must talk about Newton's law of gravitation, right? And incidentally, I am also going to be your lecturer for gravitation. Yay! So I'll save the joke for them, right? I have a joke for this. Okay, never mind. I just tell you now, since it's late at night and we all need a chill. When I was younger at your age, I've never understood why girls like guys who are bigger size. Oh shit, this is going to the recording. So when I saw the law of gravitation, I'm like, oh, I understand now. It's because I'm not big size enough. Because you see, the law of gravitation states that if my mass is big, someone else will be attracted to me with a larger force, right? So then the other way to actually attract your friend is to actually get close to him or her, right? It all makes sense, right? So you see, Newton is already thinking that far ahead, right? Teaching you how to find a good friend. Right. So anyway, the main idea is, however, that the universal law of gravitation is that the force is proportional to the product of masses and inversely proportional to the square of the distance between them. Okay. G is given by this constant. Don't worry about it, we'll give you in your formula sheet. So let's say we have two planets, M1 and M2. There will be a mutual attraction. All right, and the force of M2 on M1 is the force of M1 on M2 by Newton's third law. So this is actually the Newton pair laws, right? Newton's third law, the pair forces. So as much as I'm attracting you, you are attracting me right now. Agree? Just that the force is so minuscule, because our mass is so small that we do not feel it, right? Even though our distance is only like 3 meters, but our mass is so small, times 10 to the power minus 11 is so small that it hardly moves us around. Okay. Right, some features, well, boring stuff. Okay, yes, this one you need to know, right? The last one. If due to spherical symmetric object can treat it as a point mass, and the entire mass is concentrated at center. For non-spherical shape, this equation does not actually hold true. Right, so you must be very careful when using this idea. You have to break it down into components of forces and you integrate over that whole area. And that makes it a lot difficult. And that is actually in your question 21, which is really painful. But anyway, these are some of the things that I wanted to show you if I had time, but I don't have, so moving on. All planets move with elliptical orbits with the sun as focus. The radius sweep out from the sun is equal areas, equal time intervals. What does that mean? Right. Third one is the one that we talk about very often. The square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. Right. Should I even talk about this? The elliptical orbits, right? You can actually find the two foci here, and you actually draw this, right? It goes in this shape, right? This being a string, right? And this can move around this string. So you imagine a string linking this point and this point, and this is a bead. You move the bead around, you actually trace this shape. Okay, the perihelion, peri means like periscope, right? Means when you're closer to the sun. Aphelion, I'm not sure what other names there are. It means you're furthest away from the sun. O being the center, right? I mean, not exactly center, but this is the distance, equal distance from the center. This is the two foci. B, right, is a semi-minor axis. A is a semi-major axis. Right, you can construct the ellipse in this manner. Okay, this is not strictly within your Olympiad syllabus. Right? It's nice things to know. Second law is that the area swept, right, will be the same. Right, for the same time interval, the area swept will be the same. Right, even if you see, because here the velocity will be very slow, here the velocity will be very fast. Right, for the same time, this will sweep a bigger arc, this will sweep a smaller arc, but the areas will be the same. Right, this is what you will learn later on in the fourth lecture, right, of angular momentum and conservation of angular momentum. Third law, this one you need to learn how to prove, and it's actually in your H2 syllabus. Basically, you just equate gravitational force to centripetal force. Right, work it out, you get this. Basically, it says that the period of orbit squared is proportional to the radius cubed. That's it. Okay? I think I should stop here, right? Because there's really not enough time. With this, go and do 20, no, just go and look at 20, 21, 22, 23, and 4, and 5, okay? I'll go through that next lesson, but you can look at it ahead of time. If you have any questions for the rest, please come down. Please go and look at 21 in advance. You will need to look at it in advance because it's really difficult. 22 also. Right, the rest should be okay. Alright, that's all. Thank you.